So let's continue our discussion on mass defect. So I had given you a rough idea of mass defect. Now we will move on towards our actual idea of mass defect. Okay. So the mass of the nucleus. Okay. The mass of a nucleus. It is slightly lesser. Okay. It is slightly lesser than the sum of the masses of isolated individual nucleons. Sum of the masses of isolated individual. So mass of the nucleus is less than the sum of masses of isolated individual nucleons. That implies there is a mass defect, right? Mass of the nucleus. I had told you already that if you consider that these are the individual nucleons and this is suppose your nucleus formed out of these individual nucleons. Your nucleus is being formed out of these individual nucleons which are over here. Then when you add the masses of these individual nucleons, suppose there are 5 in number, then mass of this first nucleon plus mass of this second nucleon plus mass of this third nucleon plus mass of this fourth nucleon plus mass of this fifth nucleon, it should be equal to the mass of the nucleus in classical mechanics. According to classical physics, the mass of this nucleus should have been equal to the sum of the masses of these 5 nucleons. But in reality, the sum of the masses of these 5 nucleons is greater, and the mass of this nucleus formed out of these 5 nucleons is lesser, slightly less. Mass of this will be slightly less, and mass of this will be slightly more. So this is called as your mass defect. The mass of a nucleus is slightly less than the sum of the masses of isolated individual nucleons. That implies your mass defect. Now rarely in some cases, in case of some in case of some unstable nucleus, rarely in case of some unstable nuclei, an increase in mass is also observed. Okay, an increase in mass is also observed. Now what does this mean? This simply means that if suppose there are some nucleons and this nucleus is formed, then in some rare cases, in case of some unstable nucleus, the sum of the masses of this individual nuclei will be smaller than the mass of this nucleus. Means energy will be converted into mass in the case of this. Okay, energy, for example, over here I had told you in the previous class that some of the mass was lost in the form of delta E is equal to mc square. Some of the mass was lost, but over here in the form of delta E is equal to mc square, some of the mass which will be in excess, the mass of this nucleus will be little bit more than the mass of these nucleons out of which it is formed. So delta E is equal to mc square. When you apply the formula, that will give you that how much energy was required. Okay, unstable nuclei case this is. Okay, unstable nuclei case. So in this case you will have to give the energy. Okay, give energy in this case, in this particular case. So it will lead to formation of an unstable nucleus. Okay, so this is a rare case. An increase in mass is also observed, and this is what is called as your mass excess. Okay, mass excess. This will be called as mass excess. Now consider a nucleus. Consider a nucleus. And its symbol is like this: A, X, Z. Okay, like this is the nucleus. Then what is the sum of the masses of the nucleons? Sum of the masses of the nucleons. Now do not call this to be the sum of the masses of nucleons. This is not your sum of masses of nucleons. This is simply your addition of number of means total number of nucleons. This is your number of nucleons. Okay, which is the mass number. But we are talking about sum of masses of the nucleons. Means we are taking the point value also. We are taking the point value also. The sum of masses of the nucleons is equal to what will it be? Mass of protons, all protons, plus mass of neutrons, all neutrons. Okay, but you know this very well that number of protons is your Z. So Z is your number of protons, and mass of each proton is suppose mp. So the mass of total mass of protons will be Z into mp. And number of neutrons, how is number of neutrons given? Number of neutrons n is given by a minus z. Okay, number of neutrons n is given by a minus z. So it will be capital N m n, right? So because capital N is the number of neutrons and mn is the mass of each neutron. So capital N into small m n will be your mass of all neutrons. So this will turn out to be something like this. Okay, where you know this very well, where where mp is equal to mass of a proton, mn mass of a neutron, and your a value is very clearly z plus n. This is quite obvious, so that implies your n is equal to a minus z. Okay, number of neutrons is equal to atomic mass number minus atomic number. Okay, now if suppose if suppose mn, capital Mn, is equal to isotopic mass of resulting nucleus, isotopic mass of resulting nucleus. So Mn, capital Mn, is your isotopic mass of resulting nucleus. Now what is the resulting nucleus? The resulting nucleus is the one which is being found. Okay, the resulting nucleus is the one which is being formed out of Z protons and N neutrons. The resulting nucleus is the one which is being formed out of Z protons and N neutrons. So suppose Mn is its isotopic mass, the isotopic mass of this resulting nucleus. And I had told you one thing very well, that this Mn, okay, this Mn, okay, this capital M, capital N, means this one in the blue box over here, this Mn and this atomic mass number A, most of the times, in most of the cases, suppose 17.018 is the Mn value, then A value will be 17. Okay, suppose 16.0182 is the Mn value, then A value will be 16. So such is the relation between them. Okay, so isotopic mass usually has the same integer value as the atomic mass number A. The isotopic mass usually has the same integral part. Integer part is same, okay, as the atomic mass number A. But the atomic mass number A will always be a full integer, full figure, and the isotopic mass Mn will be always a point figure. Okay, it will never be a complete full figure. In some of the cases I had told you that C12, O16, in those cases Mn comes out to be coincidentally equal to your atomic mass number A. But usually this Mn, capital Mn, is usually a point figure, not a perfect figure. So capital Mn is equal to isotopic mass of resulting nucleus. Okay, then what happens? Then clearly, as this will be your mass defect case, okay, this will be your basically mass defect. So we are not taking mass excess case, because in the case of mass excess the nucleus is very much unstable. So we are taking the generalized case of mass defect. So this is your isotopic mass of resulting nucleus, okay, capital Mn, and this is what, this is your sum of the masses of individual nucleons. What is this? This is your sum of the masses of individual nucleons. Means you have summed up the masses of Z protons, you have summed up the masses of Z protons and A minus Z neutrons, means capital N neutrons. Okay, so you have summed up their masses, so it is your sum, and your isotopic mass is your capital Mn. Okay, so this is greater, slightly greater than your capital Mn, because of mass defect, because some of the mass has been lost in the formation of this nucleus. Okay, as it was an exothermic process. Okay, so from here, in the case of classical mechanics, if we talk about classical physics says that these should be equal. Classical physics says, but relativistic physics told us, and the real fact is that the sum of masses of individual nucleons is slightly greater than the isotopic mass of the resulting nucleus. And this slight reduction in mass, because its mass is slightly less, so there was some of the mass which was converted into energy by the formula E is equal to mc square. Okay, so so the decrease in mass, what is the decrease in mass then? So the decrease in mass can be written like this. Okay, from here the decrease in mass can be written like this. So the decrease in mass, so decrease in mass, that is mass defect, is equal to your delta M is equal to, now what will be the mass defect? This is suppose 11.7 and this is suppose 12. So your decrease in mass will be 0.3 kg mass has been lost by the previous example, hypothetical example. Okay, so that will be your decrease in mass. Okay, so let me see over here, just a second. Okay, yes. So decrease in mass, that is mass defect, is your delta M is equal to ZMP plus A minus Z Mn, and it will be minus Mn. Okay, minus M, capital N should be there over here. Okay, so this is your, suppose, equation number 1. This is what is your mass defect. Now let's assume, let Me is equal to your mass of an electron. Mass of an electron, suppose. We are converting this in the form of an H atom. Okay. Now our job is to convert this formula in the terms of mass of an hydrogen atom. Okay. Mass of an hydrogen atom, neutral hydrogen atom, and mass of a neutral atom. Okay. Suppose this is some, this will be the nucleus of some element, right? This will be the nucleus of some element. Suppose it is the nucleus of neon 10. Suppose it is the nucleus of neon 10. Then what's our job right now? Our job is to write this in terms of the mass of neon atom. Okay, not nucleus. Nucleus mass is M, capital Mn. Okay, we want to write this formula of delta M in terms of atom of neon, neutral atom of neon. So neutral atom of neon, will consist of additional 10 electrons. Okay, because neutral atom will consist of 10 electrons and 10 protons. Okay, so there will be additional 10 electrons in it. So those 10 electrons mass we will again add. Okay, in order to denote the delta M in terms of the atom mass. Okay, instead of nucleus mass. Okay, so Me is equal to mass of an electron, suppose. Then equation 1, तो हमारा जॉब अभी यह है कि जैसे ये किसके टर्म्स में था, नियॉन के न्यूक्लियस के टर्म्स में था. ओके, तो हमको इसको नियॉन एटम के टर्म्स में कन्वर्ट करना है. ठीक है, ये जो कैपिटल Mn है, मैंने थोड़ी देर के लिए मान लिया कि नियॉन एलिमेंट का न्यूक्लियस था, या कोई भी दूसरा मान लो, कैल्शियम मान लो. ठीक है, तो ये जो है ये कैल्शियम के न्यूक्लियस के टर्म्स में फॉर्मूला लिखा हुआ है. हमको इसको कन्वर्ट करना है, कैल्शियम न्यूक्लियस के टर्म्स में ये फॉर्मूला लिखा हुआ है. हमको इसको कन्वर्ट करना है कैल्शियम एटम के टर्म्स में. तो कैल्शियम का जो एटॉमिक नंबर होता है 20 होता है, तो 20 प्रोटॉन्स होते हैं उसमें, और मास नंबर 40 होता है. तो इलेक्ट्रॉन्स कितने होंगे? इलेक्ट्रॉन्स भी न्यूट्रल एटम में, एटम की बात कर रहा हूं मैं, न्यूक्लियस की नहीं. न्यूट्रल एटम में 20 इलेक्ट्रॉन भी होंगे एडिशनली. तो एडिशनली 20 इलेक्ट्रॉन भी होंगे जो ऑर्बिट्स में होंगे न्यूक्लियस के आसपास, जो यहाँ पे कंसिडर नहीं किए हैं, यहाँ पे कंसिडर नहीं किए हैं. तो उनको भी हम जब कंसिडर कर लेंगे, उनके मास को जब ऐड कर लेंगे उन इलेक्ट्रॉन्स के मास को, तो यहाँ पे एटम का मास आ जाएगा न्यूक्लियस के बजाय. समझ में आ रही बात? सो दैट्स अवर जॉब. So that's why we are doing these mathematical manipulations. Let Me is equal to mass of an electron. So equation 1 may be written as, so how will you write the equation number 1? Then equation 1 may be written as delta M is equal to, okay, your ZMP plus Me. This means you are adding and subtracting ZME. Okay, what is this? You are basically, you have added this term, you have added this term, and you have subtracted this term. So adding and subtracting the same term, makes no difference to the equation. Adding and subtracting the same term makes no difference to the equation. So ultimately the equation has remained the same. But the benefit of this equation is that over here you can see this clearly, that this is the mass of 1h1 atom, not nucleus. Okay, I am talking about atom. Mp plus Me is the mass of 1h1 atom, because what is there in 1h1 atom? One proton is there in the center and one electron is there in the orbit in 1h1 atom. So this will be the mass of 1h1 atom, one proton plus one electron. This will be the mass of 1h1 atom. And what was Mp? Mp was the mass of nucleus of hydrogen atom. Small mp was the mass of nucleus of hydrogen atom. But as soon as I add the mass of an electron over here, so it gets converted into the mass of atom instead of nucleus. Okay. So I can further do some mathematical manipulations over here like this. For example, Mp plus Me I can write as Mh. Okay. So let me write on the next slide. Delta M is equal to your Z Mh, capital Mh, mass of hydrogen atom, right? This will be written as mass of hydrogen atom. So I wrote it like that. And plus A minus Z remains as it is. Okay. Over here do one correction. Yes, it is correct only. Okay. Plus A minus Z. This remains as it is, Mn. Now look at this carefully. This is the mass of, you have added Zme. That means you have added the electrons also in the mass of nucleus. This was the mass of nucleus, isotopic mass of nucleus. Now this isotopic nucleus had Z protons in it. Okay, so number of protons is equal to number of electrons in a neutral atom. So you have added the Z electrons mass. So as you have added the Z electrons mass, this will be the mass of atom instead of nucleus now. This total will be the mass of atom instead of nucleus now. So suppose that, let that be represented by Mx. Okay, neutral atom. So let this be equation number 2. So where Mh is equal to mass of an 1h1 atom. Okay, and Mx is equal to mass of neutral X. Okay, Za atom. Okay, now we have neglected the small difference which appears on account of the binding energy of electron. See, during the formation of nucleus, from individual nucleons, when nucleus is formed, there is some energy lost in the form of delta E is equal to mc square. Okay, but at the same time, when a nucleus when electrons and nucleus combine, when electrons and nucleus combine, some of the energy is lost in the form of binding energy between these electrons and this positively charged nucleus. So some of the energy is released in this process also. In the formation of neutral atom also. So in the formation of neutral atom also, some energy is released. but that energy is very small as compared to the formation of nucleus out of individual nucleons. The formation of a neutral atom releases much less energy as compared to the formation of a neutral atom releases much less energy as compared to the formation of a positively charged nucleus out of individual nucleons. Okay, so as this releases much less energy, so the binding energy on account of electrons will be much lesser as compared to the binding energy on account of formation of a positively charged nucleus. Okay, so that's why I will write one statement over here. Okay, a small difference, a small difference appears due to binding energy of the electrons. Since atomic binding energy is typically atomic binding energy is typically of the order of several electron volt, and the nuclear binding energy is of the order of several mega electron volt. So we neglect the small energy or mass difference we neglect the small energy or mass difference Be by c square due to electrons. Okay, what is the Be by c square? The binding energy will be equal to your mc square. Okay, so take the c square over here, so Be over c square will come. Okay, so that is your mass lost. That is your mass lost. So a small energy difference appears due to the binding energy of electrons also. Due to binding energy of electrons also, since atomic binding energy is typically of the order of several electron volts, I have told you just now, and the nuclear binding energy is of the order of mega electron volt. So this is electron volt and this is of the order of 10 to the power 6 electron volt. Mega electron volt means 10 to the power 6 electron volt. So we neglect the small binding energy mass difference which it creates. Okay, so some of the mass is also lost during the formation of a neutral atom. Okay, so when a neutral atom is formed, when this when suppose, let me write over here, suppose this plus Ze nucleus was there, and suppose Z number of electrons. Okay, Z number of electrons come. Okay, a lot of electrons, suppose Z in number, come and start revolving around this nucleus. Okay, start making, not revolving, start making motion around this nucleus, suppose. Then during the formation of this neutral atom out of this positively charged nucleus and these electrons, during the formation of this neutral atom out of this positively charged nucleus and electrons, this will also release some energy. Okay, this will also lead to some mass defect. This will also release some energy, and the mass defect will be given by this Be by c square, but this will be of the order of electron volt, and the formation of this plus Ze means the positively charged nucleus, this plus Ze, the binding energy of these neutrons and protons when added together, this will be of the order of mega electron volt. So this is quite huge, so we consider this only, we neglect the binding energy of this. So this is what is meant by this. Okay, so thank you very much. Now we will do the binding energy in the next class. Thank you very much. Jai Hind, Jai Bharat.